Hi everyone, my name's Ash Davies. I'm a Kotlin and Android GDE in Berlin, and I'm going to be talking today about refactoring code with confidence and using test fakes, or why mocks are bad, part 2. So, going to put this in the situation. You've just joined a new company, landed a sweet new job. Got all your computer set up, you got all this fancy swag, and you got your coffee maker set up, and you got this all thing. You sit down with your new team, and you're ready to start working, and you sit down with the code base, and that's when you see your new project. So the reality is that we don't always have the luxury of working in green fields. We're often inheriting legacy code, and we're often working with code that we maybe has inherited a lot of tech debt. And because that generally is the reality of other things we're working with. Production quality projects often come with a complicated backstory and a history of backlog and technical debt. So it can be really kind of tough to know where to get started with legacy projects and with legacy code in general. And you're probably all quite familiar with legacy code already. Hopefully, that's why you're here today. Most importantly, it's because of this level of uncertainty. How do we proceed with a project that we are not certain with? We don't know how to go forward. And this is the crux of the problem. The uncertainty means it leads to undeterministic behavior, unpredictable behavior, and it's difficult to predict and difficult to test. And it's easy to judge and say that this code sucks because it's unpredictable. But what are the causes of these things? What does unpredictable code actually look like? Well, a lot of this comes from a level of coupling. Coupling was also a sitcom in Wales, I think, from Friends, which is quite funny. But coupling actually describes how interconnected modules are often interacting with each other. It's often compared with cohesion. So a highly coupled code is sort of difficult to separate. It's really interconnected and really kind of difficult to understand. And it makes it harder to find a seam with these things. Conversely, loosely coupled code is a bit more easily structured, easy to understand, and it means there's a limited API surface. So there's less going on in between these different modules. Very well diagrammed here from Wikipedia, showing how good loosely coupled code has high cohesion. So it works really well in its own module. It works really well with its interconnected parts, but it has a very strictly monitored and restricted API surface where it actually interacts with other parts. Another symptom as well is going to be inheritance. You've probably often heard the argument of composition over inheritance. Composition is not just a fancy new UI toolkit. It's also a method of structuring classes. So you can have inheritance where you have derived classes and base classes. This is represented in Java and Kotlin as abstracts. And it's often as an attempt to sort of reuse some behavior. So maybe you've seen like an abstract activity class where some common behavior been pushed down into the abstracts. But this actually conceals and obfuscates this behavior, and you can't actually then find out what's happening. Say, for example, if you're then extending from an abstract fragment all the time, you're kind of hiding this behavior, and then you're chasing down a bug, trying to figure out what the hell's going on, only to find out that it was in some abstract class that was hidden from you the whole time. So this further adds to the unpredictable nature of our system. And one of the most important ones I'm going to touch on today as well is the topic of mutability. So unnecessary mutability introduces change into our system. By the very nature of being mutable, it makes our system mutable. This undetermined change causes unpredictability and unreliability, and it makes it more difficult to assert the correct state of your application. And carrying on from this, unpredictability. Unpredictable code is by definition difficult to predict. It's difficult to assert your expectations, difficult to replay and predict the behavior. And this is often caused by a topic of polymorphism. This is where code can have different execution paths and it does different things based on the different input. And it's very difficult to ascertain what the structure or what the intended code should be. You can compare this as well to kind of backup code. So what's often determined as resilient or kind of failure sensitive code where something could possibly go wrong actually ends up adding noise to our system. It's a bit harder to understand what's going on. So there are many approaches to sort of dealing with these problems and dealing with these issues presented to us. And ultimately, our goal as an engineer is choosing the right tool for the job. There's not a single silver bullet here. It's just knowing what tools you have available to you and choosing the best one for the job. So I would like to highlight a topic of extreme programming. This is sort of extreme coding practices coined a little while ago. and it sort of takes some best practices to a bit more of an extreme level. Some consider it a poor use of time, for example. Oh, it's going to take longer to do this if we follow all the best practices, and I need something to work right now. And now I understand that, and I sympathize that sometimes you need to make compromises to be pragmatic, but it's really useful to consider these practices, even if you're only doing it in some small portion of your time, sort of to help improve yourself, improve your skills as an engineer, through coding katas, through exercises, pair programming. Really good, really useful to kind of practice these things. So a lot of common practices might be pair programming, where you're working closely with a colleague or a member of your team to kind of work on an individual topic. This places a high level of scrutiny on what you're working on, and it's really useful for very complex tasks. Also, it makes you feel kind of really fancy. I wouldn't recommend the top hat, but it does help. There's test-driven development as well, focusing on writing the test before the implementation. This is common with the red-green refactor process. Very important to kind of try this out. I understand that maybe it doesn't work out all the time in production environments. It's one of the tools at your disposal, and it's really useful for things that need it. And one of my personal favorites is offensive programming. So this is where you actually kind of embrace failure as an option. If your system is failing or if something is going wrong, this is an acceptable state. If something should never happen, then you don't need to guard for that. So things like unnecessary checks or polymorphisms or fallback code, fallback behaviors, these are kind of often sources of errors. And if your error is being thrown somewhere deep in the stack trace, it's difficult to find this place. But, for example, inversely, if your error is being thrown at the point of failure, it's very easy to find out what's going wrong and fix it. And it's really good to actually disprove developer assumptions as well. So another great tool at our disposal is Kotlin. So one of the guiding principles of Kotlin is to make it easier to write good code. This sort of encourages developers by making it kind of uncomfortable to write bad code. I really like this idea. Like, as a British person, just making people uncomfortable is one of the things I do very well. And the primary tenet of this is the concept of mutability. So, what is mutability and what are the risks of mutation, sorry. Take this contrived example, for example, and we can assume that taking in a mutable list. So this example is by nature impure. It takes the mutable list and it mutates the world around it. Now, of course, you might never write a function like this, and I would recommend that you don't do this, but it's a contrived example. It produces a non-deterministic state. It mutates the world around it. And given a different list, it's going to produce a different result each time. So it's hard to predict. And this is often relevant when you're working with Java code as well. So for example, the date class is actually by nature mutable. So you can then pass that upstream and then have your upstream consumers mutate it, and then that's introducing unpredictable state into your environment. And that's the crux of the problem really here, is a shared mutable state is the root of all evil, right there with money. It causes race conditions, non-deterministic behavior, and it's often mitigated with things like mutexes, thread-safe confinement, and semaphores, and all these fancy coding structures and coding languages. But ultimately, a better architecture is going to help you most best with these things, And it's going to ensure like you have a predictable state. This state can be replayable, reproducible, and easy to predict. What you want to go for here is a unidirectional data flow. Now, you might have heard this term a lot when used with architectural paradigms like MVVM, MVI, MVP, MVZ, MVX. Ultimately, it's not that important which paradigm you go with, as long as you're striving for a unidirectional data flow, keeping immutability. That's what's important. So for example, Kotlin takes collections and makes sure that you actually have to explicitly mark them as mutable. So it makes a separation between a normal immutable list and a mutable list. But what's important to remember here as well is that these might often be backed by a Java implementation, which is mutable. So you could, of course, just cast it to a hash map or something like that and then mutate it. What I recommend doing as well is, especially if you're working with Compose, is to use the Kotlin immutability library, persisted lists. And this will ensure that you have an immutable library. And it works really well with Compose because you no longer have to mark things as stable because Compose will know that it cannot change and it will not then try and recompose your setup. Another part of this is the IntelliJ IDEA IDE itself. So built with Kotlin, of course, these little nudges that sort of push you in the way of being a better engineer. So just looking at this, you have an immutable value and a mutable value. And the mutable one is underlined. And I don't know about you, but just looking at that makes me uncomfortable. Like, it makes me like, I want to change it. So these nice little kind of pushes in the right direction is what Kotlin is doing really well. Another one you might notice is final concretions. So by default, classes in Kotlin are marked as final. And this was a very intentional design decision. And it does, of course, make things difficult for testing, but it means that this is encouraging composition over inheritance. So with all these things at our disposal, the most ultimate tool we have at our disposal is testing. Automatic testing acts as a safety harness, and it gives us confidence in this code. It gives us confidence in refactoring, and with that confidence, we can protect ourselves against regressions, give ourselves early feedback. But when we're working with a legacy code base and a lot of legacy code, it can be kind of difficult to know where to start with these things, because poor code is often synonymous with poor architecture and poor testability. So if you're looking at a piece of code and thinking, how on earth do I test this? Well, it's probably not written in that way or in a good enough way for you to be able to do that. So, we have to start with refactoring. So it's not really my goal to persuade you to write tests. Hopefully, if you're here today, it's because you like testing and you want to find out how to do that better. So testing, of course, comes in most commonly two approaches, the manual or automatic, much like driving, I guess. Manual can be performed by QA engineers or developers to verify or reproduce errors manually by actually using a physical device. Whereas automated testing runs on a CI, takes the form of unit or integration tests. And these are insanely more powerful because you're protecting yourself against regressions. These tests are running every time on every iteration. And it's really important to kind of build a complementary test setup where you have a comprehensive test suite for a robust regression. Now, my personal preference is to start off with unit tests, but there's a lot of recommendations for UI tests, server tests, integration tests, smoke tests, monkey testing, fire testing, everything you can do. But make sure you have a good unit test setup. So as I said, it can be a bit difficult to know where to start when working with legacy code and working with unit tests, because it's not until we start writing our unit tests that we find out how difficult it is and how poorly structured our code may be. And this is often a sign of code smell. Because most established code bases have like a long and colorful history of design decisions and tech influences, and this accumulated tech debt composed of anti-patterns, code smells, and just poor decisions and drunk code. And it's because of this we sort of need to do some refactoring in the first place to get even started with unit testing. So in order to refactor with confidence, we have to write some unit tests. But in order to unit test, we have to refactor our code in the first place. We find ourselves in a bit of a catch-22, a deadlock, if you will. So we have to kind of find a bit of a compromise. So we need to refactor without actually changing the behavior. And this is what we want to do with introducing what we call seams. Seams are the separation between two pieces of fabric. Everyone here is wearing clothes, I hope. And it translates similarly with programming. It's the logical separation between two pieces of code. And there are many different language-appropriate techniques for finding these seams, for introducing things. You can adjust your class path, you can mutate your state, you can do all these weird and wonderful things. But the most reliable way of doing this with Kotlin is through object refactoring, and that's what I'm going to focus on here. So this allows for the kind of replacement of dependencies and behaviors without actually modifying the implementation. So the most common type of refactoring is utilizing the compiler configuration. So take the example of this fit filter, which instantiates a new parser in the actual class as a variable. We can refactor this so that it takes in this parser as an actual function. So this is a nice technique that I quite like to use, using functional interfaces and factory functions. So here you're kind of moving the implementation and putting the dependency on the actual injected parameter. This is what's called as dependency inversion, often relied upon with dependency injection. And IntelliJ offers like a really nice array of options and tools of actually achieving this. So you only have to do the refactoring autocomplete thing here, and you'll find out you can extract interfaces and move things around. And it's really easy to do this with a few clicks. And being automated, you can be a bit more confident in that it's going to do it safely, rather than you putting in a typo or if you're tired or something. So Dependency injection is not to be confused with dependency injection frameworks, such as Dagger or the lesser valued Coin. Fun fact, Coin is a service locator, not a dependency injection framework, but I'm not going to get into that argument today. But dependency injection is a coding paradigm. It's an approach. It's not just a framework. Fun fact, you don't even have to use Dagger to use dependency injection. This is just a way of writing code. So you might refactor this code to instead take the dependencies in the constructor. Fun introducing the favorite thermosiphon example. Everyone loves thermosiphons. So reducing the behavior is another mechanism. So here we got the actual original dependency, which was a thermosiphon, and then we're defining like a more narrower type of a pump, which does fewer responsibilities, fewer things, and then we're taking in the actual responsibility that we need, rather than relying upon a kind of higher level concretion about something that does more than what we need. Narrowing the scope thereby reduces the dependency, thereby makes it easier to replace these dependencies and reuse your code. Kotlin offers this nice way of dependency injection by having these dependencies in the actual constructor. And this means we can actually start with seams because we've created this logical separation between our two pieces of code, and we can start unit testing. And so for some tests, we might want to actually respond with different dependencies. But why is that? So unit tests particularly should be fast. They should be running in milliseconds, not seconds. So expensive dependencies should be replaced. It's probably a little bit overkill to try and achieve nuclear fusion for a unit test. You might have stateful dependencies, things you use running on I/O, writing to disk, fetching from network. These things are by nature unpredictable, and you're not be able to predict the state there. So you want to make sure your tests are actually idempotent. So disk operations are stateful; they can change. Further, you might have some dependencies which are maybe a bit more error-prone, maybe a bit they need to be refactored, but not just yet, or they're obsolete, or you just can't rely on them just fully. So you want to be able to change them to something else. So this introduces the concept of test doubles. Test doubles are a common technique for refactoring, which replacing dependencies offer simplicity and isolation of control. Most commonly, mocks. Mocks are a type of test double that allow you to specify expectations of interaction and often used to verify that interaction with dependencies. So given this class we've got under test here, we can give it some mocks, and we cross our fingers, throw some salt over our shoulder, sacrifice a goat, pray to the gods, and we run our test and hope. But of course, this isn't going to succeed because mocks don't do anything. They're just empty objects that do some runtime reflection to actually create this proxy instance. So you have to actually add this whole configuration to mocks to actually have this implementation. Now, mocking libraries have an extensive DSL for building all these different things and asserting behaviors. But with that extensive DSL and with that extensive API come a lot of foot guns. Now, they are a powerful tool, but it's so easy to shoot yourself in the foot or in the face. So declaring a mock is kind of complicated. And because of that, you kind of open yourselves to a lot of unpredictability and API sensitivity. And you've got this thing like accidental invocation. So if you're spying on a real object and you're asserting the behavior upon that, then this on do answer BDD syntax is actually going to invoke the real object. So if you've got an empty list and you're saying when it gets the first element in that list, it's going to throw because, well, there's no list there. I'm not going to say why mocking lists is shown here. You should never do this anyway. But the point is, it's a contrived example. More importantly, it introduces API sensitivity. So creating runtime implementations is rarely type safe. If the API changes, the mock is still going to compile. So given this refactor, for example, you're adding a new function to that class, but the mock is still going to compile because you've not actually added this functionality. So these further changes are going to be ignored. So perhaps your test is now expired, it's stale, it should be refactored, but you wouldn't know that because it's using a mock. Another approach I've seen is to actually use mocks for data classes. Don't. Yeah, I don't do that. And as well with the sensitivity part is that it's difficult to know where you're providing a return value from. Say, for example, you have a deep stack trace and you've got mocks upon mocks upon mocks upon mocks. You might be tempted to use default answers. Default answers will provide smart nulls, or there's lots of different types of things doing there. I implore you, please do not use this. Every time you return a mock from a mock, God kills a kitten, and I like kittens. So yeah, we should really, really avoid this. But what I find kind of really ironic about this whole situation is the reason we were using mocks in the first place was to avoid these expensive dependencies, like these kind of difficult things to construct and difficult things to build. And then we ended up kind of replacing these very expensive dependencies with very expensive mocks. We've got all this kind of weird sort of hacketry going on with runtime code generation, bytecode manipulation, and reflection. With all these different things, and it seems like we're replacing one problem for another when we had the solution all along. And the real problem with this as well is that it introduces dynamic mutability. Now, it might be a minimal impact here because maybe you're writing a test for the first time, you think, oh, I just need to go fast, and you think that mocks might be an easy solution, but they doesn't scale well at all, and you're going to find yourself having these problems further down the line where you have this dynamic mutability. It's harder to predict what state your mocks are actually in your unit test. So in your actual unit test here, you've already got a state, which is, how can I ascertain against that? I would be a terrible cat owner if I didn't use this opportunity to show you my cat. This cat is named Kotlin. So yeah, this was a great photo. He was just sitting on the breakfast bar with a really judgmental pose, and I use it in every presentation. Cotty knows it's bad. So should you. Dynamic mutability is the root of all evil. So this concept that I've touched on many times here about unpredictability, it's a really underrated metric. Much like tech debt, it's hard to quantify, and it's going to manifest in lots of different ways. So it's going to manifest in an increased learning curve. So when you're onboarding new colleagues, it's going to be difficult to kind of onboard these people. If you're refactoring code yourself, it's going to be difficult to kind of ascertain what your system is doing. And most importantly, it's going to have issues with peer review. It's going to take longer for your code to actually get reviewed. And because if your colleagues can't actually figure out what your code is doing, it's going to sit there for ages, and it's going to slow down your development time. It's going to introduce the risk of bugs, because unpredictability means you can't predict the edge cases. And most importantly, for the managers in the room, it's going to slow down feature delivery, which is going to slow down your income and your bonuses. So tech debt is going to have to be repaid at some point, because this unpredictability is not just harming new colleagues, for example, or junior developers, or other people in your team, but you. Like, if you've ever come back to your code after a weekend and cannot figure out for the life of you what it does, or even the next day or after a holiday, we've all been there. I look at my code after last week and I'm like, what was I thinking? This unpredictability really will hit you in the face. So there's a really good blog as well, blog entry from Google blog testing on the toilet. If you're not familiar with this, this is where in the Google offices they will have this little printout with some fact sheets and some information in the toilet cubicles where you could have a read whilst you're dealing with business. And it's really kind of a nice blog, I recommend it. But the idea here is that they recommend not mocking classes you don't own. Because if you're mocking classes of third-party libraries, for example, it's going to be unpredictable about how their API changes. Say you updated to a new version of the library and they introduced a new function or deprecated something else, but you're using mocks, so you wouldn't actually know what's going on because your interface doesn't break. And here's the thing, it's not just this that's important, because you don't own your code. From the second you push your code, it is no longer yours. It belongs to the team. And that's the really important part, is that you have to code for the understandability of your code for the rest of your team. Be considerate to your coworkers, because this is going to come full circle and hit you in the face if you're not. If your code is introducing cognitive complexity, it's not good code. I've written code all the time which I thought, oh, this is a really clever use of language functions. And then I come back to it a week later and I was like, what was I thinking? You need to keep things simple. It's most important to be understandable more than it is to be clever. And that's where the concept of keep it simple, stupid comes from. One of the core fundamental understandings of this is that with mocks, you're verifying the interaction, not the outcome. It doesn't matter if the invocation was correct if the result of the operation was false. And at some point, you're actually just testing the language. This point actually deserves its own talk, but I'm going to kind of brush over it a little bit. There was a great talk yesterday on behavior testing as well. Check out the video if you haven't checked it out yesterday. So, for example, we're using mocks, okay? Maybe there's mocks already in place. What do we do? Like, what's the alternative? What other options do we have? Well, mocking libraries provide a very extensive DSL for building runtime implementations of your classes. But you know what else has an extensive DSL for building runtime classes? Kotlin. So you might have already actually used stubs, or might have seen stubs in place as well. And these are a simple implementation only meant to actually allow your code to compile. Really simple, should have no verification or behavior in there, just operational behavior as necessary to actually kind of happen. Really is running a little bit out of time, so I'm sorry for keeping you from your lunch. But stub implementations are kind of utilizing Kotlin idiomatic code to make it a bit more kind of seamless and make mocks redundant. Also introduces API sensitivity. If your dependencies change, you have to then change your test code, which you should have to do because your assumptions have changed. Your test code has changed, and it needs to reflect that. So this change will not compile because we've changed our interface, we've changed our dependencies. And we know this because we wrote it, and we're not reliant upon a framework. But what if you need a bit more than a stub? Well, we've got fakes, and we can use fakes to verify the outcome. You can pass a lambda, for example, to kind of introduce this testing behavior, and it additionally keeps a list of outputs and incomes, and you can then assert that on what you're doing. The nice thing about this is because you write it, you can actually have it perform the validation that you need to do. So you are the person best qualified to actually understand the domain behavior. And if you need to add additional behavior that's maybe not handled by a mock, instead of using some weird, complex, archaic API, you can just write some Kotlin code and have it do what you need. So fakes are ideal because they give us the most control of the situation about our assertion and what we're doing. But you might ask who is responsible for writing these things. Mocks are easy because your library is generating these things for you. Well, the answer is you, because you are the person most qualified to deal with this. Uniquely qualified because you have the understanding, the domain knowledge at the time of writing your code. And you're going to have more knowledge than either yourself next week or a junior developer or someone else in your team about why this code should be like it is. And then these fakes then perform additional documentation for that. Many circumstances, actually, it's quite sufficient to actually provide an in-memory implementation of your mock. Given a simple store interface, we can just store this in memory. It's all good. And then you can have some basic in-memory implementations. Sorry if I'm going a bit too fast. I'll share the slides later if you want to check it out. But this is all just kind of sample code that you can use to verify your behavior. So like Kotlin encourages us to use better practices by making poor decisions more uncomfortable, we can use better practices to make better decisions and better interfaces and things like that. So you might have heard the concept of interface segregation. Now, of course, solid design principles is a bit of a tired trope, but it's still relevant today. So by using these things, you might have like a huge interface that you need to mock. It's going to be hard to do that. And that in itself is a source of code smell because your interface is doing too much. If it's difficult to fake, it's difficult to understand. So you want to keep your interfaces lean without too much responsibility and too much going on there. And by making it a little bit more uncomfortable to write our tests, we can actually then push ourselves into better behavior and having more understandable code in production. But Android, you might say, we have a lot of stuff to deal with that's legacy. And whilst there have been a lot of advances with Jetpack, with Android X, and Project Mainline, we still have to deal with some things like context. Context is considered by many to be a God object, where you have a lot of independent or distinct types and unrelated methods. And since this interface or abstract class commands so much, it's very difficult to test it. So of course you have to take this with a grain of salt that, maybe I can mock context, maybe I can do this. But consider that you shouldn't have mocks for all the things. So let's recap this. I wanted to recommend this as an extreme coding principle because extreme coding you might not be able to employ all the time. Maybe you have to make some pragmatic solutions. But it's really good to consider this as an option. And knowing the tools that you have available to you is our job as a good engineer to make sure we're making the right decision. Choose all of your options appropriately. Shared mutability should be avoided like the plague. Do not rely upon this. Your goal is to achieve an immutable unidirectional data flow and to then use test doubles sparingly when necessary only. So things like mocks, which use voodoo and black magic to provide implementations at runtime, and you've got spies and stubs and fakes. All of these are tools at your disposal. So make the right choice and don't use mocks. Thanks.